Hello everyone, welcome back to our channel. In today's video, I'll be explaining about the applications of metal organic framework in different fields. So, so to begin with, I would give you a brief introduction about MOF for those who have coming back or it is like a brushing up. So metal organic frameworks, in short, it is called as MOFs. So these MOFs are of hybrid porous molecules. So MOF consists of two things. One is called as the name suggests, it contains a metal part, which is this, and there is an organic part. So the metal part is called as a metal nodes and the organic is called as a linker. So usually in metal organic framework, there is a node and there is a linker. So you can choose a different kinds of a metal or you can choose different kinds of an ligand or an organic linker in which to link those and get an extraordinarily amazing structures as you see it here. You could see this is called as a MOF5, which is called as M metal organic framework 5. So if you create a MOF and you have a and it is similar to some structure, you can name it if you create a new MOF, and this is MOF 117. You could see that this is a different organic molecule benzene with two linkings, and this is called as an here is a center benzene and then you have three other linking benzenes in it, and this is a little more complicated organic structure, and this is MIL 101 and this is MIL 53 and this is the ZIF 100. So these uses different organic substrates or linkers. Also, this used in different metal nodes. And you could see that PCN66. It is a very interesting morph, and it is very useful for an drug delivery as well as a sensing molecule. And you could see it has got a lot of functional or organic parts in it, and these makes them highly stable as well as highly rigid. And this is MOP1 and DO morph. So these are different structure of morphs, and just wanted to highlight, like when you Google it around, you would see these structures, and these structures, please do not confuse with by looking at the structures and think like, okay, this is a complicated thing. No, it is not a complicated thing. The blue or the polyhedras are of a different colors. This is because of the preference from the author, and then you have some molecules going inside, and these molecules are nothing but an organic substance. So and then you have a void. So the space in which inside the morph which is accessible is given by a void. It is either in yellow in color or in a different color, which is in this case it is red color, and here it is yellow, here it is light yellow, and these two are also yellow. And in some cases it may be left blank also. It doesn't mean that if it is left blank, it is not porous in nature. No, morphs are porous in nature. Maybe the surface area is less, and they would explain if the pores are not accessible. And this is a typical structure of a morph. I have zoomed it to give you an elaborate structure, and you could see that this is the organic part which is linking a metal center here as well as a metal center here. I would change the color so that yes. So here is a metal center and here is a metal center, and these metal centers are linked by an linker. So that is why it is called as linker or an organic moiety, and then the metal center. So the first structure forms is in 2D structure where it forms like a square, and this square is extended in this third direction. So for a morph, it extends in first it forms extends here and then it here. So this becomes a 2D structure, then it goes for the third direction. So this is called as a 3D morph. And there are also morphs which is called as a 4-dimensional morphs. So these morphs are also called as 4-dimensional morphs. So the term fourth dimension is a very new concept, and it is very imagined for few people to understand. It is like a 2 dimension is like, let's say like you have a length, breadth, and then the height. So length, breadth, and the height. And the fourth dimension is when the length or the breadth or height, each one of the term, either one of the term is movable or it changes. So that is a it can be called as a fourth dimension. And fifth dimension is adding of those fourth dimension elaborating. So I'm not going into classical explanation of 4 dimensions. Just imagine if a molecule is able to change its shape over the period of time, this is called as a fourth dimension MOF or four-dimensional structural differences. So here are I'm going to list few examples of the applications in which the MOFs are done. One is it is used as a gas adsorbent, or in technically can be called as chemisorption, not physisorption. So MOFs does chemisorption. Also there are examples of MOFs which has physisorption also. And then it is used as a redox catalyst or redox material, where it accepts and gives electron based on the environment in which it is there. So it can be used as a cathode, or it can be used as an anode material. So it finds its application in reduction of carbon dioxide, methane, water splitting, batteries, and a lot more. And optical activity, which means it tends to gives the optical activity like second harmonic motion, laser ablations, or it responds to the heat in which you give and gives out as an optical signal, or the optical signal is converted into and something called as a heat signal. Or there was an example in which they have used it as an hyperthermia treatment, which means like they change the magnetic field around the MOF, and because of which it gets heated up, and thus it gives us the use for hyperthermia, which is used for treating cancers. And MOF can also act as a host molecule, which means it can bear some molecules, like it can take up drugs and then it can give out when you stimulate the MOF to give out. So it is not just for a storage of drugs, it can also be used as a delivery system. And next is an enzyme carrier. So it doesn't just carries the drug but also enzymes. And for those who work in the bioinorganic or biomedical applications, you would know that a drug is a different structure and an enzyme is a different structure. So enzyme is a big structure, and drug is a small structure, and the structural difference of enzyme and drugs are very complex to compare. And the host molecule should be ready enough to pick up those and then deliver it wherever you want. And next, it can store nanoparticles in it, like there are pores inside the MOF which can accommodate nanoparticles and have different applications like magnetic separations, or it can be used as a catalyst to enhance some reactivity of reactions, or you can put some magnetic nanoparticles into it. Now suddenly the MOF becomes a magnetic attractive particle, still keeping its old properties same. That is where the MOF's beauty is. So when you put a magnetic particle into it, it just takes up into its pores. It takes up into its pores, but still retaining its old property. For example, a MOF is acting as a catalyst. So when you put an iron magnetic particle or a palladium magnetic particle, the it doesn't change its catalytic activity, or the catalytic activity is very less reduced or impacted, but it would also have an property of a magnetic now. So these are used in gas separation or a catalytic separation, as well as in hyperthermia, where if the MOF is active for cancer active, they just make it to an magnetic MOF, then it can be called as an hyperthermia active drug. And carbon dioxide reduction, and this comes in under catalysis. And then you have it is used as a sensor, and it is also used in electronics applications, which is technically the extension of the sensors and MOFs. So here I have come up with four different applications in which I would highlight. So the first application is it is like gas storage. So the MOF would take up some gas and then it would store it. So uh, the main thing is it takes up, stores, and then it delivers. That is a very important thing. And next application is it is in selective separation. So when you have a molecule A and molecule B, it takes up and then just allows one to pass through but stops the other one. So this is called by separators. These are used in gas separations like carbon dioxide, methane, and nitrogen, carbon monoxide, all these. Also, you can also separate liquids by it, like styrene, and then different conformations of styrene, like one is allowed, one is not allowed, xylens, and all those examples can be done here. And it can use as a sensor or a selective sensor. For example, if someone wants to detect an, let's say like carbon dioxide, and then in the fumes, they just make a sensor with the MOF, and then when the carbon dioxide is sensed or observed, it just gives out an electrical signal, and these electrical signals in turn are detected by the sensors or the electronics and then gives us as an electrical signal. And the next application is like it is used as a catalyst. So when you have A and B molecule coming inside, MOFs brings them together to form a new product and then gives out the end product. So this is called as a selective MOFs. So I'm going to highlight on the first application, which is called as gas storage. So one beautiful thing is the pores close upon desorption. So what does it mean is when you supply a gas molecule into it, it takes up, and then it takes up to a certain extent in which it has been the volume is, and if you put more excess, it wouldn't take it. For example, let's say like there is a MOF which is of like a rectangular pore. So when the gas molecule comes filling inside, what happens, the shape of the molecule just extends, or the pores is changed. Let's say like it becomes an oval shape because of the change in the structural, because of accommodating the gas molecules. So now the molecule cannot enter. The the pore size and then the pore shape is different. So this is the previous one and this is the end after the adsorption of certain amount of gas. So now it can be called as closed pore, which means the pore is no more capable of taking up the molecule. So it can be engineered to take only certain amount of a gas, not to any extent, and it has an ideal delivery capacity. So which means it just doesn't store, it also gives out when you require it. And this is a very very key advantages as compared to the other rigid adsorbents like silicas, aluminas, zeolites, where the structure of those are very defined, it would not change, which means that there is a more of physisorption happening than the chemisorption. When you have a structural change where and then the pores can be closed or gates can be closed, these are called as physisorption activity. So there is a chemical connectivity between these two, because of which it can be called as pore closing, and then it can also be used as delivery. And where do you find these applications? It is very highly used in this hydrogen fuel cell generation. So we need to store hydrogen and give out only when there is a requirement. We know hydrogen is a highly flammable gas. So it was very, so once you are able to stimulate it is in the room temperature, we would soon have hydrogen fuel cell cars. Like now we have battery cars, battery powered engines. So similarly, in soon we would end up having this hydrogen fuel cells when the gas storage technology is commercialized and it is feasible. The next is carbon dioxide adsorbent. So there are two reasons to adsorb carbon dioxide. One is to convert into something useful chemicals like methane, ethane, or higher carbon numbers, and to remove as a pollutant. Then water purification. We know like water is a very important substance around the world, and it is very very necessary for any living being to survive on earth. So it involves in water purification. You see, these are gas and this is a liquid, and methane in liquid state at low temperature or in a gaseous state, this can be used for separation of these molecules. These are few examples of those. And next is the highly selective separation. So there was a very beautiful sentence, so I just put it here. The selective response of the porous host in the adapting the pore shape to recognize gas molecule species leads to a significant increase in the absorption selectivity as compared to the rigid adsorbent. So what they say is there are rigid adsorbent which I have selected it said before, and these rigid adsorbent, what does it do means it just adsorbs, but in this case the pores recognize what is the gas molecule and coming in. So because of which there is a separation happening. So there was a report from Long et al. So they have said near perfect separation. This was their title from their paper, so which was published in JACS. So this was they said that it is near perfect. We know like carbon dioxide and methane. So carbon dioxide is C double bond O, dipole moment is 0, and similarly you have methane. This is CH4 tetrahedral structure, and the dipole moment is 0. So you see the electrically both are same. So it doesn't have, and separation of this double bond as well as methane CH bond is very tough. because it is a single tetrahedral molecule. So chemically they are stable. So but they have designed a MOF where cobalt and benzene pyperidazolate organic linker, and these are flexible in nature, and this is a flexible MOF. That is why it is called as a 4D MOF. So it helps in the good separation of carbon dioxide and methane. This is a very important thing when someone is doing converting carbon dioxide and methane. So conversion of carbon dioxide to methane involves not 100% conversion. So which means the produced product has impurities of carbon dioxide. So until and otherwise you are able to separate the impurities, it is not easy to get 100% pure methane which can be used as a fuel. And this was published in JAX. Sorry, like you could see it now. The yes, this is the yes. So this is the publication in which this has been reported by Long et al. So it was reported in JAX in 2018. If you are interested, you can go have a reference to it. And this is the next example where they have separated propene from propylene. You know, propylene is a very important polymer which is used in preparation of polyethylene or polypropylene, and then propylene glycol as well as some polymers. It is used as an tape or sheets, but it often the raw material of propylene comes with always propyne. So you could see that the structure, it has got a double bond and this has a single triple bond in it. So structurally both are rigid in nature, and there is a CH3 molecule here, and here is a CH3 molecule. So technically you have a carbon multiple bond and attached with a CH3. So how will the MOF recognize this is a carbon-carbon double bond and this is a carbon-carbon triple bond? You see, like chemically these are almost same. There is a multiple carbon bond and there is a and then a CH3 is attached. There is a multiple carbon bond and a CH3 attached. So there is a very small difference in its chemical reactivity as well as in the physical appearance. Let me say like less than 20 Armstrong would be the difference in the bond length. So that makes them off very interesting. So this was also possible to do it, and I think the details in the paper says that it was possible to separate 99.999 percentage accuracy. So which means it is very highly efficient. So 99.999 percentage of purity of propylene was separated from propyne. So this is very good. So MOFs are used as in very such brilliant separators. And I think yes, here is the this is the reference in which it was reported in 2017 in JAX. These work where the propylene and propyne separation, this separation has been reported in this if someone is working on it. And this can be used as smart sensors, as I was saying. Suppose like you see like the molecules like carbon monoxide and nitrogen are chemically similar. There is a molecule atom A, atom B, and there is a triple bond between them and two electrons. So how will a sensor select these molecules? How will the sensor know this is nitrogen, not carbon? And the dipole moment and the electronegativity are very quite similar. So these are chemically similar molecules, and both are, except that carbon monoxide has got high affinity whereas nitrogen has got less affinity towards iron. So they have exploited this property, and then they were able to build a sensor or an electronic device in which it would sense not just carbon monoxide but nitrogen and gives you a different signal. So materials with the ability to open their pores only for one type of molecular species results in the specific recognition. So it recognizes the molecule, it acts as a sensor and recognize the molecule and gives out a signal. So MOFs can be used as in selective sensing. And next is it can be used as a switchable catalyst, which means that the MOF exposing its active sites during the pore opening system. So let's say like we have designed a molecule, a very brilliant molecule like nanomaterials. Nanoparticles are very popular catalyst and it is very efficient for them to have a catalytic activity. But MOF can also be like that. If you build a 2D or a 3D MOF, what will happen is it is a rigid structure where the active sites are accessible, and so this is called as a rigid structure. But what is a dynamic structure? So one dynamic structures are those structures or molecules in which it changes shape only when you require it or only during a certain environment. Let's say like humidity is more, then the MOF opens up its pores or changes its pores, and then it becomes active for the catalysis. Or in the presence of some gases, suppose let's say like we need to do only carbon monoxide conversion or not nitrogen conversion, or the nitrogen need not be absorbed on it. So the molecule would sense only the carbon monoxide, then the pores changes, and then the carbon monoxide is let in, and then the catalysis is taking place. So these are called as switchable catalyst, or it can also be called as smart catalyst. So these are the next generation catalysts that are being developed developed. So these advantages of having this catalyst to develop in such a smart way was possible only with MOFs, and especially switchable catalyst or smart catalyst has been a very important area in which it has been explored now. So that's all. I have highlighted 4 applications of MOFs, and there are many more applications of MOFs which would be coming in part 2. And just remember that MOFs have got huge potential and you just keep exploring it. For example, you built a MOF for gas purification. Sometimes it can use as a very good sensor. Just try finding out someone and just test few basic tests to check if it is a really a good sensor or not. So sometimes it is very good. So just remember MOFs has a huge potential and keep exploring. Happy reading, happy researching. Have a good day.